Hello everyone, I will present to you today our mobile app called Remini, which performs blind image restoration. The contributors to this project are Lorenzo Collodi, Andrea Pesare, and me, Jelena, Rodic. Alright, so let's get started. The idea of our Remini app is to restore old or low resolution images and make them high quality. So it is a one-tap app where a user gives an old image as an input and gets a high quality, high resolution image as an output, like the one on the right on this image. So to achieve this goal, we have built multiple AI models which perform different tasks, and they all work synchronized together in achieving that one goal that we have, and that is high quality output. All right, so while we were doing this, of course, we ran into some challenges, and now let's discuss on how we handle them. In order to train our models in a supervised approach, we need pairs of low resolution, high resolution images. And the biggest challenge in super resolution problems in general is that those pairs don't exist in real life. So our approach was to start from high resolution images and try to model the real world degradation that happens at the moment when the images are being taken. And this degradation model consists of multiple components, among which are the unknown degradation kernel that we want to model, some downsampling, some additive noise, and other things that we will discuss more in detail later. Another challenge that we faced is a need to balance between reconstruction of details and generation of details. What does this even mean? Reconstruction implies recovering information from the original image in a faithful way. Those are details that actually existed in the original setup. Generation, on the other side, implies hallucinating new details that are not present in the original image or are too degraded to recover. And we want to do this because there is not enough information in the downgraded image to get a high resolution recovery. And that is why we need AI. AI helps us to naturally fill the gaps and information that we lost by learning from hundreds of thousands of other images it was trained on. So now we'll talk about methodology and the pipeline that Remini has. So we have four major parts: face enhancer, background enhancer, face detector, and image blending unit. And first we need to explain why we need a different face enhancer, a different background enhancer. So when users look at the image, they pay most attention to faces. This is natural. And that is why it is important for us to achieve the best possible result we can on the faces. So when a human looks at a very low resolution image of somebody else's face, they can estimate many details very well because they know what a face should look like and where some key features should be, because those are some common components that each face has. And we wanted to teach the neural network to think in this way, and after training it on a huge number of faces, it finally can estimate those details like a human can, like the texture of the skin, eyes, all of those details, and it can do it better than the background enhancer, because the background enhancer needs to learn how to work on various materials, clothes, environments, everything, and it is not specialized for the specific task of faces. So that is why we need different networks for these tasks. And also, now that we established this, we need a face detector to crop the faces from the original image and feed it to the face enhancer. And we also need, in the end, the blending unit, which will help us combine all of this back together in a natural way. All right, so let's go a little bit more into detail with all of these components. So first we will talk about the face detector. And as I said, the job of this model is to detect and crop the faces from the original image. And also it needs to do the alignment of faces, which means to center the crop around the tip of the nose, and also, if necessary, to rotate the faces in the right way so that they are standing vertically, because it is important for the face enhancer. because it learns how to hallucinate details in a relatively fixed positions. So the eyes, the nose, everything should be around the same points in the image. So that is why this is important. And for this task, we used retina face architecture, which is a type of a convolutional neural network, to achieve this goal. So now let's go to the most important component of our app, and that is the face enhancer itself. As I explained earlier, we're trying to leverage the fact that all of the faces have some similar features. And the biggest challenge we have with the face enhancer is that we cannot let the model hallucinate too much, because we need to preserve the identity of each face on the image, because everybody wants their face to have its true original characteristics once they see the image, right? And here you can see some examples of how our face enhancer works. In the line above, you can see the inputs, and on the line below, you can see the outputs of our face enhancer. But what I want to show you now is the architecture that we used for this model. So it consists of three major parts. And the input image is a face crop, which is always interpolated to the same input size. And then that input image first goes to the feature extractor, which is part of the model, which learns how to embed RGB data into high-resolution features. And then these feature maps go to the context extractor. Context extractor basically learns how to get contextual deeper features, and it has a very large receptive field, which gives exact positions of eyes and nose and important key points, also facial symmetry. It gathers all of this information for the face enhancer, and then it feeds it to the face enhancer unit, which uses all of those features to restore the original image quality by learning the face prior, and by this it is being able to hallucinate the details of the face based on the encodings it got from the context and feature extractor, and then it can do it in a realistic and preserving way. Alright, so now let's go to the background enhancer. As I explained previously, background enhancer needs to work in various types of situations, and it does not have any reference points where to start from, like the face enhancer had. So it can be working on a lamp, or it can be working on somebody's arm, on kitchen tiles. It can be literally anything. And another difference that exists between the face and background enhancer is that now we need to focus more on the fact that the final image should look realistic, meaning that when you look at the image, it doesn't have an artificial touch to it, and that is more important for us right now than faithfully recovering the details of a lamp. It needs to look like a real lamp, but it doesn't have to recover every single detail from that exact lamp which was in the setup. So now we should also mention that the model for background enhancement is the slowest part. It's the most computationally expensive part because it needs to process the full image. And we'll talk about optimizing this model later on. First, let's discuss the degradations that we mentioned before. To be able to train this network, as I said, in a supervised approach, we need low resolution, high resolution couples of images. And these pairs don't exist in real life, we don't have them, so we need to create them synthetically. We do this by modeling the real world degradation that happen when people take images. So, to obtain this realistic degradation, we have several steps. The first one is try to blur the image in different ways, then try to downsample images with different kernels, then add some additive noise that also happen in real life, and finally compress the image. So we mix all of this on different images to best estimate how degradations happen in real life. So once we do all of these steps, we have our data, and then we are ready to train our network in a supervised approach. Regarding the architecture that we used, this one is called Real ESR GAN, which is kind of a generative adversarial network, which has RRDBNet components or blocks inside. Okay, so I mentioned that we needed to work on the optimization of our background enhancer model. And the reason for this is because our app requires to deliver output very fast, and it is an important issue in our pipeline. The time is an important issue. So since the background enhancer works on the whole image, it is slower, and we needed to do some optimizing. So the first thing that we wanted to keep in mind is that we need to preserve the achieved quality of the background enhancer that we had in the original model, but we want to make it faster. So first what we did is quantize the model, which achieved double the speed. Then we used distillation to remove from the original model all the unnecessary weights and leave with the smallest possible model, which can generate the same or very similar results to the original one. And finally, we did the conversion to ONNX and achieved the final speed up of 5.5 times compared to the one in the original model. So now we have enhanced faces, we have enhanced background ready, and what we want to do is to put the image back together. And the problem here arises in the fact that the face enhancer and the background enhancer don't always enhance same part of the image in the same way. And if we want to just plainly stitch them back together, the merging points would be very visible, and the difference in texture in that part around the face where the face enhancer worked on but actually belongs to the background, like this part on this image here, will show, and the texture will be different, and this is something that we do not want in our output image. So that's why we need the compositing model. And our compositing model has two parts. The first one is alpha matter, and the second one is Laplacian pyramid blender. So let's explain each one of them. For the alpha matting model, it gets an input crop of the face, and what we want is a mask that gives each pixel a probability that it belongs to a person or it doesn't belong to a person. So to achieve this, we used ModNet architecture, which is actually a tree map free and guidance free method for alpha matting. What does these terms mean? Tree map free means that we don't have an image of the background without the people taken just a moment before. Guidance free means that we cannot ask our users to interact with the image and click on the parts that belong to people or not. And all of these things are very usually used for the alpha matting problems. So for us, it was a little bit harder because we only had the input image, and we should get the output, which is a perfect mask where humans are. The second part is Laplacian pyramid blending, and once we have the masks and have the faces and have the background, we can do stitching them back together. And we want, on the edges of the mask where the stitching will happen, we want a natural transition while preserving all of the details in the original image. So we don't want just to blur it or do something like that. So for this, the ideal approach was Laplacian pyramid blending. And here we have an example on a very simple one, which shows a very simple mask, which is just cut in half, and we want to merge this apple and this orange together. And here you can see that Laplacian blending is able to achieve a very natural transition here. So this is what we want on the edge where the people are compared to the background. So this is what we use to stitch it back together. And finally, once we have all of this, we have our final output image, and we can see an example of a result like this one. So on the left, you have an input image into our app, and on the right, you have the output image which Remini gives us, where you can see that all of the details are enhanced in a very natural way. Also, the faces are preserved. Everything is stitched back together in a seamless way. So this is the final result. One more thing that I wanted to comment on is some quantitative improvements that we were able to achieve. Since we cannot use standard metrics like LPIPS or PSNR to measure how high quality our models are, we turn to our users and we look at the metrics like retention rates, which means how much users come back to use our app, or revenues, or number of saved images per user, number of edits per user. All of these metrics show us how good our app is and how good our models are. So every time we have a new background enhancer or a new face enhancer or any part of the app that I mentioned before, what we want to do is an A/B test and then see how our users interact with the app, and based on that quantify if we have a better model or not. So on this image, you can see that we have these green dots. These green dots represent metrics for the new background enhancer. They represent average number of edits per user for the pictures that don't contain the face. This is very useful for us if we, for example, are looking at a different background enhancer. So the green line represents the new ones, and the purple dots represent the control segment or the current version of the app. So here we see that the background enhancer, the model with the new background enhancer actually has better number of edits per user. So we are satisfied with this result, and this means that we will actually use this model in Remini and replace the old background enhancer that we had, because with this one we achieve better results. Here on the slide you can also see the metrics that we had for different parts of the network, which we changed. And finally, we got the current app, which you can now see in the App Store. That would be all from me today. Thank you for your attention, and you can check out our poster.